Okay, we're still busy with the bipolar junction transistor chapter. The next section that we're going to do is the BJT as an amplifier and as a switch. We've mentioned earlier, mostly the transistor is used for amplification and for electronic switching. Anyway, let's go and look at the circuit diagram of a basic transistor amplifier with the AC source voltage Vs and a DC bias voltage Vs and a DC bias voltage VBB superimposed. Figure 421 in your textbooks. Alright, important before we go and look at this specific circuit is to have a look in your textbooks or at how to identify DC and AC quantities in this specific textbook. So I just want you to read through and mark this section as well on page 180. DC and AC quantities. Please take note, I have mentioned it as we worked through this section, how the voltages and currents for DC and AC are used in this book. So let's stick with it. You can see in this text italic capital letters are used for both DC and AC currents. As you can see there, I and V italic. This rule applies to RMS, average, peak to peak AC values. AC current and voltage values are always in RMS unless stated otherwise. Please underline that. Especially very important when you're going to do calculations and you want to show me some waveforms on the oscilloscope. So what can oscilloscope cannot show me RMS values, for instance, né? So if you are given a voltage as say a source voltage, if I go and look here at the specific diagram, you have to go and calculate, for instance, a source voltage was here given as say 10 millivolts. So it was given there as 10 millivolts. I immediately know that if there's nothing mentioned, this is an RMS value. And if you have to go and show me the maximum and minimum values of that waveform there, you have to know that you have to convert it to peak values. So take note of that as well. Make a note somewhere so that you don't forget that. DC quantities always carry uppercase, a non-italic subscript, as we've seen, like for instance the VCC that's applied. I can see here VCC, it's a voltage, and the subscripts capital letters. VCC indicates that it's the supply voltage for at the collector. So, and for DC, for AC voltages, let me just see, there's an AC voltage. I can see that VC there is a lowercase italic subscript letter to indicate an AC voltage. But read through that section, familiarize yourself how the DC and AC quantities are addressed in this book. Alright, let's carry on with the amplifier. Remember, we've seen that a transistor is used as an amplifier or as a switch. The very first thing, and we will discuss that in detail in the next chapter, is before I amplify any signal, I have to bias my circuit. Now, we've discussed biasing a lot, and you've also done biasing in the previous sections on the diode and so forth, and very important, we're going to do biasing with our amplifier circuits as well. Anyway, the biasing at this stage, when we will learn different types of biasing in the next chapter, is I have a voltage VBB and I have a voltage VCC. My biasing will be done with VBB in this case, so I will adjust, or I will use a certain VBB to give me a certain current IB on my transistor there. I can refer back, we will discuss this in more detail later, but in the meantime, just to make you think about this, remember we talked about the characteristic curve of a transistor, IC against VCE. Um, and then we've plotted the transistor. We will discuss that again just now. The transistor being used as a switch at cutoff and saturation. Connected 2 lines, that's called my load line, and I know that I will use my amplifier, my transistor as an amplifier in this region, which is called the active region or the linear region. But I've also seen when I've drawn the family of characteristic curves with the transistor, different IBs will give me a specific IC. So for a certain IB, I will get a certain IQ, a certain IC, and that will cause a Q point there. That is the biasing, but we will discuss it in much more detail. So once I've biased, then I will add the signal that I want to amplify. So that signal that I want to amplify will be superimposed on that IBQ that I've done there, but much more detail about that. So I can see that my transistor is already switched on. It is not in cutoff. My transistor is switched on by biasing before I start amplifying. And then I can see that I will be able to get linear amplification. So after I bias, as I can see here, then I will apply my input signal riding on my VBB or IB, which causes a certain IB. And then the output will be taken at the collector for my amplifier. You can see here at VCE, it's actually VC, but VCE and VC is the same thing because there's no resistor at the emitter as mentioned earlier. And I can see, and we will discuss this later on, that from my input signal, I can see that my output signal is amplified, although it's 180 degrees out of phase, which we will also discuss in later lessons. So that is the transistor being used basically as an amplifier. And then what I also want to determine is I want to determine how many times that my input signal get bigger. That is called the voltage gain. How much did it gain? So I will have to be able to determine the voltage gain of this amplifier. How many times did it go bigger? You can refer back there to page 181 in the textbooks, and it discusses it there by using the formulas that we have basically discussed already for VB, VC, because I can see from the circuit, if I refer back to the circuit again here in the textbook, I can see the input is applied at the base and the output is taken at the collector. Now there's VCE. Alright, so to get this ratio, the voltage gain is a ratio. It will be the output divided by the input now, which is VC over VB. That's why if you go and look at the formulas here, I want to determine VB and I want to determine VC. So in the end, I can see here the voltage gain is VC divided by VB. And then by substituting, VC is equal to IE times RC, and VB is equal to IE divided times R accent E. And the two IEs cancels out, and I'm sitting there remaining with the voltage gain formula of RC divided by R accent E. That's the maximum voltage gain that an amplifier of this kind can achieve. Okay, but we will discuss that also in much more detail in later lessons. That's basically just an introduction to amplifier operation. As I said earlier, we're already in the next chapter going to do all the biasing circuits to be able to do amplification and so forth. Just take note of that as well. Since RC, the resistor on the collector, is much larger than the value of R accent E, the output voltage for this configuration is greater than input voltage. So I can see that the amplifier do amplify now. Okay, in the example there is just an example to show me how to determine the voltage gain. Voltage gain there, RC divided by R accent E. RC in this case 1 kilo ohm divided by 50 ohms, and I have a voltage gain for this specific amplifier of 20. So the output signal is 20 times larger than the input signal. But it isn't always this simple. In later lessons we will see how to do this more accurately. Then BJT being used as a switch, we've also been introduced to. But here's a whole section on it, just to revise again. There's the transistor, and there's the equivalent of a switch. When the transistor is in cutoff, it acts like an open switch, and we've seen what are the parameters then. What are the parameters? The parameters are IC and VCE. No? So that is the current flowing through the switch IC, and VCE is the terminals, collector, emitter, where my switch is over. Okay, so when it is in cutoff, we've seen that the value of an IC, because of the formula that says IC is equal to beta DC times IB. I can see there, of course, if IB will be equal to 0, as I can see here, IB is equal to 0, then of course IC will also be equal to 0. VCE, on the other hand, if I measure over this open switch, what am I actually measuring? If I can redraw the supply over there, then I am actually measuring value of VCC. So the parameters for cutoff is IC is equal to 0 amps and VC is equal to VCC. On the other hand, at the closed switch, then the transistor is in saturation. I can see here that the switch is now closed. If I go and measure over there with a voltmeter, I should ideally measure 0 volts, but we've seen it's not an ideal device. We've also mentioned that for a transistor, and especially used in this book, we assume it to be approximately 0.2 volts. And the current that flows through this device will now be maximum current, and we've seen the maximum current is called IC sat. So the parameters of a transistor used as a switch, and it is a closed switch, so IC is going to be equal to IC sat, maximum current that my circuit can deliver, and VCE is going to be equal to VCE sat, which we assume to be approximately 0.2 volts unless otherwise stated. Alright, but we can see this in the textbook again if we refer back to the textbook. There they are, equations 4.8, conditions in cutoff, conditions in saturation, equation 4.9, and equation 4.10, the minimum value of base current needed to produce saturation, I can also calculate by getting the value of IC sat and beta DC. So IB min is going to be IC sat divided by beta DC. Normally, IB, you can underline that last sentence, normally IB should be significantly greater than IB min to ensure the transistor is saturated. But anyway, go and work through the example there. It asks there, for instance, at 4.10, for the transistor circuit in figure 424, what is VCE when V in is 0 volts? Second part, what minimum value of IB is required to saturate this transistor in beta DC if beta DC is 200? And look here, neglect VCE sat. Always read the question, because if that isn't written there, then of course I cannot neglect the value of VCE. The last part there is calculate the maximum value of RB when V in is equal to 5 volts. So you will see there's just an application of the equations that we've learned. VCE is VCC is 10 volts. How to determine IC sat. Remember now they specifically said to neglect VCE sat, so otherwise it would have been VCC minus VCE sat, which we assume normally to be 0.2 volts and so forth. Alright, the last thing here is there's a simple application of the transistor as a switch. It has been asked in exams before, so please note there, in this specific case, if I can get to the figures here again. What I have here is a square wave input wave that switches on for 1 second and switches off for 1 second. So if the question asks you draw the circuit for a simple circuit of a switch transistor being used as a switch with an LED, and you can see then here, if the square wave is applied to the base, it will drive the transistor into saturation by exceeding the minimum base current, as we've seen in the previous example, how to calculate this, to drive the transistor into saturation and switch the diode on. Remember to look at the LED's limitations as well, to switch on the LED for intervals of 1 second on, 1 second off. Simple application there to switch the transistor on and off at 1 second intervals. There's also an example in the textbook that you can have a look at. The question asks, the LED in figure 425 requires 30 milliamp to emit a sufficient level of light. Therefore, the collector current should be approximately 30 milliamps. For the following circuit values, determine the amplitude of the square wave input voltage necessary to make sure the transistor saturates. Use double the minimum value of base current as a safety margin to ensure saturation. Remember, we've said earlier, I'm limited by my circuit for the maximum current. So at some point, I can increase IB as much as I want, but IC cannot increase because of the limitations of my circuit, as we've seen. IC sat is equal to VCC. I've got a set voltage minus the saturation voltage of VCE, 0.2 volts, divided by the resistance, whatever the circuit may be up to this stage, RC. Right, that's the limitation of my current for my circuit. So even if I increase IB anymore, remember that formula of IC is equal to beta times IB is no longer true if the value is higher than IC sat. Anyway, in this specific case, the following circuit values determine the amplitude of the square wave input voltage necessary to make the transistor saturate. Use double them. Okay, I've read that already. VCC, and then they give you all the values. Then here I can calculate. Remember now I've got a voltage drop over the LED as well. IC sat is VCC minus VLED minus VCE sat. They told us to assume VCE sat is 0.3 volts in this case. That's why you always have to read the question. Divided by the resistance, in this case only RC, and I get that current. So IB min will then be IC sat divided by beta DC in this case. To ensure saturation, use twice the value of IB min, which is then 1.29 milliamps. Then use Ohm's law to solve V in. So IB, VRB over RB, which is V in minus VBE over RB, and then I can solve V in by mathematics. In the end, I can determine that the V in should be 4.96 volts. Work through this. It applies all the rules that you should know and some of the new rules that you've learned and equations that you've learned. All right, then again, as at the end of each section, you have to read through, work through, do the relevant questions. Basic problems up to this point is now from 24 to number 30 that you do have to finish.